Okay, I think we'll start. Welcome everybody after the lunch. First speaker is Asif Elahi. He'll be speaking on recent progress in 20 intensity mapping with SK Pathfinder in GMRT.
Sorry, the title has changed. So I had made the changes in the website.
It was 1 minute.
That has been changed.
I give 11-minute warning.
So okay, so this is the title. Sorry for the uGMRT observation for HERA calibration. So this work has recently been done with these people. Few disclaimers. So this is work in progress. We have just got the results 1 week or 2 weeks back. And so this is the motivation for the work. So we know that 21 centimeter signal from the neutral hydrogen is very important to understand the origin and evolution of the first stars and galaxies, the epoch of reionization, to understand dark matter and dark energy at the low red shifts. The main challenge of detecting the signal is the foregrounds. We have heard a lot of talk about this. And to precisely remove the foregrounds or even to avoid the foregrounds, it is necessary to have an extremely high dynamic range, maybe of the order of 10 to the 5 to in that range of calibration of the telescope. So this is basically, we will deal with the calibration challenges of 21 centimeter signal. So I will be talking about this HERA hydrogen epoch of reionization telescope. So this is designed for the power spectrum estimation or statistical measurement of the 21 centimeter signal. And with this full configuration, it can measure the 21 centimeter signal within in 1,000 hours of observation. This is a cartoon design of the HERA, and this is one of the few antennas of the telescope. The key, an important thing of HERA calibration is that it uses redundant calibration. So basically what it means that you use the identical baselines of HERA, and you get the calibration, the gains and the unique visibilities from the measured data. So you don't need prior information about the sky. Only assume that the baselines, the beam and baselines are identical. But it leads to it boils down to there are some degenerate parameters. For example, the flux scales. You cannot get the flux scales only from this. So for that, you need some reference sky models. And that's called the absolute calibration of HERA. So this image, this plot I got, I think Nitya presented this just before a few hours. So this plot shows that if you have a better calibration sky model, if that is complete, if that is accurate in position and fluxes, if it has accurate measurement of the spectral indices and their errors, then you can use these regions also to probe the epoch of reionization 21 centimeter signal. Otherwise, we have to this foreground leakage will not allow us to probe these regions. So HERA, this upper limit result, the best results have used the GLEAM catalog, which is 90% complete at 50 millijansky. However, the completeness goes down to 50% at 25 millijansky, and its angular resolution is around 2.5 arcminute at the frequency of our concern. What we want to do, we want to use the high angular resolution of uGMRT and the wide bandwidth to have a better sky model for the HERA, so that we can improve the absolute calibration of this telescope. That is the motivation. So what do we want to do? We want to identify more sources, which are very closely separated. Also, we want to use the GMRT's wide bandwidth to get better measurements of the spectral indices of those fainter and those sources which are separated very closely. So these are the 3 calibrator sources. So now I will be going to the observation, the data that we have observed, and how we have processed to analyze the data and what are the final results. So these are the 3 calibrator sources that were identified in these works. And to identify, so this shows the full map, and this is the 150 megahertz, 400 megahertz Haslam map scaled down to 54 megahertz. This is the white region is what HERA observes. It's a deep scan telescope. And these 3 fields, which are where DGSE, the diffused emission is subdominant, have at least one strong source at the center. Strong means a source which has around more than 15 Jansky flux, and which is quite isolated from the other sources. So these 3 sources were identified, and I will focus only on this middle one. which is the 0 to hour. The array is 0 to hour. So this sources is this field is what we have observed with GMRT. This is our observation. So where this center is the GLEAM 2-hour field, and we have observed 6 pointings around the center one to get this kind of an observation pattern. So this source gives you an impression of the primary beam of the GMRT telescope at 250 megahertz, which is the highest band of the band 2. And our observation time is around 1.8 hours per field, totaling with the calibrators, it totals to around 20 hours of pilot observation. And GMRT has these two bands, these two correlators, the software backend and wideband backend. This software backend is what I will focus on. It has a small bandwidth, 16 megahertz. The wideband has 100 megahertz of bandwidth. But this present analysis is only for this GSB data. The total observation, as I said, is 17 hours, and the on-source time is 12 hours. So we have used the SPAM pipeline, the source peeling and atmospheric modeling. So it corrects for ionospheric effects. It does direction independent and dependent calibration. And after doing the calibration, we have imaged each of the fields. The imaging has been performed in APES, which is inside SPAM. And then finally, we are adding those images to get a mosaic. So these are individual pointings. Very difficult to identify the sources from these slides, but you can see in a laptop with high resolution to identify most of the sources. So this is the central pointing, and these are the other 6 pointings. And the theoretical RMS that one can have is 0.4 millijansky, and we have around 10 times more of source RMS with the 20 hours of data. The RMS varies between 2 to 5 millijansky. So this is what we got, and this after that we have added as I said, we have get a mosaic using AstroPy, and the off-source RMS has boiled down to 2 millijansky. So this is the best result that we have got with this pilot survey. This is the mosaic, and you can see there are many sources which you can found here. That RMS is 2 millijansky. Sorry for the typo. This image also shown sometime today. So this the background is shown is an image got from HERA. You see these two bright sources, other sources are barely visible. And this is what these purple stars are what has been observed with GLEAM. So you can already see that there are 2 sources here, and there are many sources for this. So there is not an isolated source, there is another source here. So this field is complicated. Here also in the center we see this same source. Also there are more structures. And also this source, I will show that there are more structures to these sources, and it is very important to model these sources accurately so that your absolute calibration has less errors. And finally, your power spectrum remains less contaminated. So one of the central region I have highlighted here. So you can see the bright source here, and these 2 sources which were not identified earlier in GLEAM. So there is recently GLEAM X catalog has been released, and GLEAM X is remarkably well, and it has indeed identified these sources. So this central source is a quasar at high redshift. We are still investigating it. What are the other properties that this source can have? So we have now made a source catalog. So this is been sorted with the brightest source at the first. So this is the brightest source, and you can see that there are 2 sources which are very close, and which is actually this source or this source. And with uGMRT, we can get a fantastic image like this. I mean, we can probe the structure of the sources, and this looks like some AGN, but we don't know actually what actually it is. It's still, we're investigating these things. So now we have also cross-checked the other properties of the catalog, how good the catalog is, whether to make it ready for to use for HERA calibration. So we have found that we have on a 50-50, the sources are 50% of the sources are point-like, and the other 50s are extended. We have also checked how much in terms of RMS we can go. We found that we have almost 50% of the image area is above 5 to 6 millijansky. So this was roughly 25 millijansky for GLEAM. For GLEAM-X, I think we still don't have the results from GLEAM-X, but this will be very close to GLEAM-X. But GLEAM-X has a much larger coverage and everything. I mean, it will surpass everything that we have, but this is a very pilot survey with GMRT. We have tested the positional accuracy of the sources, and it matches very well with TGSS, NVSS, Gleam and GleamX. Not very much with Gleam, but with GleamX, TGSS, and NVSS. We have also checked the flux accuracy. They are accurate within 10%. And this is what we try to see if we have detected new sources. So this green circles shows the sources that you can identify with Gleam. The purple one is with GleamX, so better resolution than Gleam because it has used longer baselines for MWA. And these colors are not properly visible here. The GleamX are in red. The purple one is our work. So forget about the name. I was trying to find some name for this catalog, but it's not converged to something. So these are all crosspair sources, and you can see some of the faint sources that we can detect, which is there in NVSS, but not in GleamX or either in Gleam. This is only the central 0.5 degree or 1 degree of the image. So we are still investigating the image that we have got, and yeah, that's what we're trying to do. We also use this NVSS catalog to check the spectral indices, the distribution of spectral indices. This is coming out to be around 0.7, minus 0.7, which is expected, but later we want to use the wideband data to get in-band spectral indices measurement. We also try to see the source counts and cross-check with other surveys, with Gleam at first, and then also with LOFAR surveys, because LOFAR surveys goes very deep. So we have found that this blue, you see the blue points, squares are from Gleam, has a very large sky coverage, so it has very few, the error bars are very small. And these purple ones, stars ones are from this survey. These large error bars are because there is only one or two sources in these flux around more than 10 Jansky. There are only 1 or 2 sources which are above 5 Jansky. So there are these large error bars, but mostly it is consistent with the Gleam data, Gleam source count. And at this lower end, we see that there is some, so this black dashed curve is from a polynomial fit from the Gleam survey actually. And this is actually, this trend is close to LOFAR's deeper surveys, and some of these 3 surveys are from LOFAR. We have not tried to fit our data with LOFAR because we have more data to be analyzed, and we'll have hopefully tighter constraints on these regions also. And this is possibly due to some at low fluxes we have some more corrections because only 15 or 10, 20% of the image area was below this 2 millijansky limit. So our future plan is to have a deeper image and so source count with wideband data. With wideband, we will do in-band spectral indices measurement, and also we will characterize the galactic emission to improve the shorter baselines of HERA, which is very important. And also we will hopefully do deeper observations of the same field and the other fields. So thank you for your attention.
Okay, just curiosity. How did you match your fluxes with all the other surveys out there?
You can match their positions, and in the catalog you will find their fluxes.
But they are not at the same frequencies.
They have been scaled with some power law behavior, 0.7, alpha is equal to minus 0.7.
Okay, because you motivated that one of the exercise of this exercise would be finding the accurate spectral indices. And scaling with the power law, if it gives you a 10% accuracy, then don't you think it's counterintuitive kind of thing?
So first point is that one of the measurements are very close. Our measurement is at 150, Gleam is at 154. There is hardly any change in their fluxes in that band. So that gives us the flux measurements are quite accurate. TGSS has the exact same frequency, so we can match with TGSS, of course. We didn't try to match with NVSS because NVSS is at 1.4 gigahertz. So we used NVSS to get the spectral index actually.
The NDS at the small flux densities. So it's a kind of sample variance effect, right? Can you not fold that back into the error bars?
We need to do some corrections for the DNDS. We did some corrections. So there are some corrections. detection, fault detections and corrections for completeness. We found that this has a larger correction, but still with that correction, it is not coming to the same level. So possibly because you can see from this table that the image area that has this flux is around 17%. So only 20% of the image area have the flux. So maybe some with deeper analysis, I think it will come to some the same range. Hopefully, I don't know. Yeah, but it is not showing this variance. I mean, error bars are not here.
Very, very naive question. If you go to your plot where you are showing the ratio between peak flux and total flux. Yeah. So none of them touches the line ratio equal to 1.
Yeah.
That indicates that there is some kind of smearing.
There is?
Some kind of smearing, like always peak flux is always smaller than the integrated flux. So none of your sources are point-like?
No, the point-like and extended can be, there are some noise. So noise, you have to take care of the noise. If you take care of the noise.
For the high signal to noise ratio sources, I would expect.
So these blue ones are within 2 sigma. Red ones are greater than 2 sigma. So these are the red ones are marked as extended. Those which are more than 2 sigma, they are marked as extended.
Yeah, but the blue points. None of them are touching 1.
The blue points
Except
are,
1 or 2.
Yeah. We understand that it should. I have seen all the plots where it matches the 1. We don't get it for some reason. I don't know.
Okay, I think time to move on. Thank the speaker again.